Welcome to this summary of week 1 for the online course Fundamentals of Electronic Materials and Devices. So in this summary, we will briefly look at some of the key concepts that were discussed in this week. So we started off by using Ohm's law, and based on Ohm's law, we were able to define two related material parameters. One is the conductivity, the other is the resistivity, and both are inversely related. Based on either conductivity or resistivity, we saw that we could classify materials into three major types. One is, of course, conductors or metals. Then we have semiconductors, and finally insulators. In this course, we are mostly concerned with semiconductors, and we'll also look at interaction of semiconductors with metals. We started off with metals, and we say that metals have very good electrical conductivity or very low resistivity. To understand this, we said that the valence electrons in a metal are completely delocalized. These electrons are then free to move in the solid, and when these electrons come together, they form an energy band. This band for metals is called the free electron gas model or the FEG model, which describes the energy band in a metal. So these energy bands are partially full. So we say that there are empty states or empty levels that are available for electrical conduction, which is why metals have such high conductivity. We define something called the Fermi level, which is denoted as EF, and EF or EF naught is the highest occupied energy level at 0 Kelvin. So at 0 Kelvin, all the energy levels below EF are full, while all the energy levels above EF are empty. The energy gap between the Fermi level and the vacuum level is called the work function, and work function is nothing but the minimum energy required to remove an electron from a solid. While this FEG model is primarily defined in the case of metals, we can also extend this to semiconductors and then describe an energy band model. In order to do this, we started off with silicon, which is the most widely used semiconductor. Silicon belongs to the same group as carbon, which means it has 4 electrons in the valence shell, so 3s2 and 3p2. Just like carbon, the s and p electrons hybridize to form sp3 hybrid orbitals, and there are 4 sp3 hybrid electrons. When I have 2 silicon atoms come together, each silicon atom will contribute 1 electron. They form a bonding orbital, which is sigma, and both electrons are present in the bonding orbital. The anti-bonding orbital sigma star is empty. We can extend this bonding concept to silicon solid, where we have a large number of such individual bonds. Because sigma is full, the band that is formed from the sigma orbitals, which is the valence band, is completely full, while because sigma star is empty, the conduction band, which is formed from the sigma star orbitals, is completely empty. In the case of a metal, the valence band and conduction band overlap, which is why we have one energy band which is partially full. In the case of semiconductors, there is an energy gap, Eg, between the valence band and the conduction band. So this here is the band model for a semiconductor. This is based on the FEG model, with the difference that we have a full valence band and an empty conduction band at 0 Kelvin. EV denotes the top of the valence band, EC denotes the bottom of the conduction band, and this energy difference is called the band gap of the semiconductor. If the band gap is greater than 3 electron volts, we say that the material is transparent to visible light, while if the band gap is less than 3 electron volts, we say that visible light can interact with the semiconductor and be absorbed. At 0 Kelvin, this band is completely full, this band is completely empty, but when we heat the material to room temperature, we have thermal excitation, and this thermal excitation is necessary for electrical conduction. We can classify semiconductors based on how they interact with light into direct and indirect bandgap semiconductors. In the case of an indirect bandgap semiconductor, when an electron from the conduction band falls back to the valence band, the energy is primarily released as heat. In a direct bandgap semiconductor, when this transition happens, the energy is released as light. So silicon is an example of an indirect bandgap semiconductor, while gallium arsenide is an example of a direct bandgap semiconductor. And we will see more about these materials when we talk about optoelectronic devices. We can also define something called the effective mass, which is a measure of the internal forces which is acting on an electron that is moving in a solid. So if I have an electron in a solid and I apply an external force, so this could be a potential, we know that the electron is accelerated because of the applied potential. At the same time, there are also forces acting on the electron from all the ions in the solid. The effective mass is a measure of this internal force. Again, in week 2, when we talk about intrinsic and extrinsic semiconductors and try to calculate the carrier concentration, we will revisit the concept of effective mass. For now, we note that for most metals, effective mass is nothing but the rest mass of the electron. In the free electron gas model, we can define a concept called the density of states. This is denoted as G of E, and it tells you how many states are available per unit energy, per unit volume. We can actually derive the density of states under the FEG model, and it turns out that G of E is monotonically increasing as the square root of the energy. While G of E tells us how many energy states are available, whether this energy state is occupied is given by something called the Fermi function. So F of E tells you the probability of occupation of a state at some temperature T. At 0 Kelvin, all energy states below EF are completely occupied, so F of E is 1. All energy states above EF are completely empty, so F of E is 0. So we primarily have a step function at 0 Kelvin, but as we increase temperature, electrons that are close to the Fermi level start to get or start to acquire energy and go above EF, and we no longer have a step function distribution. If E is much larger than EF, this term tends to dominate over 1, and I can approximate the Fermi function by a Boltzmann function, which is nothing but exponential minus of E minus EF by KT. This approximation will be useful in doing calculations. So we can take the density of states and the Fermi function and put them together in order to calculate the number of electrons at some energy, at some temperature in a given material. So N of E is nothing but G of E times F of E. And if I integrate this over the entire energy band, I would get the total number of electrons. We can also do this in the reverse, where if we know N, we can use this expression to calculate the Fermi energy for a metal. So These are some of the basic concepts that are related to the free electron gas model. In the week 2, we will now use this free electron gas model to calculate the number of electrons and holes in a semiconductor, and using this we will be able to define the properties of a semiconductor.